Okay. So, yeah, so what we were discussing last time, if you remember, last time we were talking about different addressing modes, right? And we have covered majority of them. We talked about register addressing mode, immediate addressing mode, to register addressing mode, direct addressing mode, and register indirect addressing mode and IO addressing mode, right? So, and what is addressing mode? If you remember from the last lecture, addressing mode is a mechanism or a way to tell your microcontroller to where to find the operands of an instruction, right? So there were two addressing modes which we have not covered. Actually, we started talking about register indirect addressing mode, but then it has some flavors. So before we talk about those flavors or variants, so let me refresh your memory about register indirect addressing mode. So what was register indirect addressing mode? Okay, again, I can go to OneNote and create a new page, week 11, day 1, right? And uh, so, so register indirect addressing mode is where what you do is that you use a register to hold address of a memory location, right? So let's say this is your memory, right? And you have a register in which you place the address of a location. Let's say address of this particular location. I'm just making up some address. Let's say 0xF0AB. So in this register, you have this value, right? This address. So the value in the address actually points to the location in memory. And this register is a 16-bit register, so which means that it is register X or Y or Z, right? And then what you say is like, for example, load from, let's say, register. When you say load dynamically, so this stands for load dynamically, and this operand is actually the pointer, any of these three register X, Y, or Z. And let's say you are saying, okay, put the result in R16. So here what will happen? Let's say at this memory location, you have value of 100. So after the execution of this instruction, X will contain value of 100, right? Right. And similarly, you can have stored dynamically. So which mean that, for example, let's say after this instruction, I say simply increment R16. So R16 will now become 101. And after that, if I say store dynamically in X, R16, so now this value will be overwritten and it will become 101. Okay. So this was register indirect addressing mode, right? Okay, so now there are some variants which we can use with this register indirect addressing mode. One of the first one of them is register indirect addressing mode with post increment. So and the other one is register indirect addressing mode with pre-decrement. Okay, so what is the meaning of post increment? So here basically what you are saying is like this is the syntax. So instead of only saying x, you can say x plus, right? So here what will happen is that uh, so I think I need to go to OneNote again then to explain this. Uh, and actually instead of like going back and forth, I can put them side by side so that yeah, we can save over time, right? So, so for example, when you say, or maybe, yeah, maybe. So now remember, what is the value of x? X is pointing to this address, which is F0AB, right? So now what is meaning of increment? Like if I say, like for example, load R17 x plus, what does it mean? It means that load the data from the memory location which is pointed by x and put that data in R17, but after that increment x. So basically what will happen that no, currently we have 101 here in this memory location, right? So after the execution of this instruction, I will have in R17, I will have value of 101. However, as a part of this instruction execution, one extra thing will happen, which is that x will be incremented. The value of x, this is x register x, right? This is register x. So its value will be incremented. So when it will be incremented, what it will become? It will become 0x F0AC, right? So I'm just writing here new value because it is difficult to write it inside the register, right? So now the x will contain this value. So this is the value contained in register x, which basically mean that it will be now pointing to the next byte in the memory location. So if the address of this byte was 0xF0AB, the address of next byte is F0AC, right? So this is known as post-increment, register indirect addressing with post-increment, right? So you can use it, sorry, my mistake. This is not SD, this is ST, okay. Store. So you can use it with both like load instruction and store instruction. And here is on the right side, you can see the figure here, like how the address is. What happens first, that whatever current value of x you have, that value is used to index the location or to point the location in memory, and the data is accessed from that location. But after reading or writing that location, after that what happens, that one is added to the current value of x here. So one is added to the current value of x, and whatever result is, it is written back into the same register. And I'm just saying X, but it can be any one of the three. You can use X register, Y register, or Z register, right? Any of the three pointer registers, right? Register indirect addressing with pre-decrement. This is similar, but it uses decrement, and like before, first the address is decremented and then you access it. So for example, if you are saying here load R19 comma minus X, so it's mean that first whatever address you have X in X, first decrement it, and then after decrementing, use the resulting address to access the memory. So here is it how it will look like. So you have the value in X, Y, or Z register, let's say, and when you are saying now when you are using pre-decrement, so first it will be decremented by 1, and then whatever result you have, that result will be used to access the memory location. Okay, and then the result of the resulting address will also be put back in the X, Y, or Z register. Is it clear? Any question? So again, you can use this pre-decrement addressing mode also with the store instruction. Again, not again, but actually, let me just highlight. I didn't say it earlier, but here is the point. There is no pre-increment variant. There is no pre-increment variant of register indirect addressing mode, and similarly, there is no post-decrement variant. So you can have x plus or you can have minus x, but you cannot have plus x or you cannot have x minus. Okay. So in post increment variant, what happens? That current address is incremented by 1, and sorry, in post increment variant, what happens is that the current value of x, y, or z is used to access the memory location, and after accessing, the value of x, y, or z is incremented. In pre-decrement, what happens? That current value of x, y, or z is decremented by 1. Whatever is the resultant address is, that address is used to access the memory location, and also that resulting address is also put back into the same register. Okay. Any questions? Okay, so let's try to do this poll. Week 10, day 2, quiz 6. Week 10, day 2, quiz 6. Okay, this one. Okay, you have 60 seconds to complete this one. Okay, I'm ending the poll here. So first statement is correct. Second is also correct. Third is also correct. Fourth is incorrect. Why? Because there is no post-decrement variant. And fourth one is using the post-decrement, y minus, right? Load R18y minus. And similarly, the last one is also incorrect because there is no pre-increment variant. Okay. So let's have a look at an example. So let's say we want to write a program that copies the value of 55 into memory location 140 to 144. So actually we want to write the same value 55 uh, at 5 different locations: 140, 141, 42, 43, and 144, right? So how can we write that the program? So first what we are going to do is that we are loading 5 into 19y as a loop counter. So we will be running a loop 5 times. And then we in R16 we are putting the value 55, which is basically the value we want to put in all those 5 consecutive memory locations, right? Now we also need to use the address, right? So what is the address of the first byte? 140 in hex, right? So this address is 6. Remember that addresses are 16-bit. So what we need to do is that we can use any of the three pointer registers, X, Y, or Z. In this example, we are using Y. So here, why there is a mistake? Let me fix it. So should be low and this should be high, right? Okay. And then what we are doing is like we are using the Y pointer register. So remember from last lecture, our X, Y, and Z, all of them are 16-bit and all of them can be accessed using low and high subscripts, not subscripts, but high and low and high variant like YL and Y high, YH high. Okay. So in Y low, we are putting the uh, low byte of 140, which is basically 40, right? And in YH, we are loading the high byte of address, which is 0x01, right? So we are loading the low byte of Y in value with value 0x40 and high with the value 0x1. So we have now loaded the address, right? And then what we are going to, so how the things will look like, or if you want to visualize how it will look like, let's say, let me quickly draw it here. So let's say this is the first byte where we want to write the value of 55, and the address of this byte is in the memory is 140, right? So what we did is that in the Y register we put value of 140, right? And then what we are doing is we are saying, okay, Now put the value of R16, whatever value we have in R16, put it store it in the memory at the address Y, and address pointed by Y, and then increment Y, right? So as a result of this, what will happen as a result of this instruction? So what value we have in R16? 0x55. So first, I'm just writing 55. I don't want to write 0x. So 055 will be written here, and then remember here we have post decrement. So this value will be now incremented by 1. So it will become, I'm just writing here, it will become 141, right? And then we are saying, okay, now decrement R19. So R19 was 5, so it is decremented to 4. And we are saying, is it equal to, if it is not equal to 0, then go back to L1. So it is not equal to 0 because it is now equal to 4, right? So go back to label L1. So and go back to label L1. What you are saying now put the value of R16 in Y, in the memory location which is pointed by Y, and then also increment Y. So R16 is what? 55. And Y is what? Y is 141. So which is basically this next byte here, right? So 141. So here at this memory location, 55 is written, right? And then as a part of this same instruction, Y is also incremented. So Y becomes 142, right? And then you again decrement R19, so it becomes 3, and you check, okay, is it equal to 0? No, so you go back to the label, or you go back to the loop, and you will keep iterating. Finally, when your loop iteration will complete, you will have 55 written in all address locations, right, starting from 140 to 144. I don't want to do all the iterations, but I guess you get the idea, how you are dynamically changing the addresses, right? So this is, if you understand, and if you are like looking carefully, you may have realized that this is different from using the direct addressing mode. In direct addressing mode, what we do, if you remember, we said load from data memory statically. And what you do is like you specify a register. Let's say you are saying R16, and then you specify an address. Let's say the address is 0x140. I'm not writing 0x, but let's say 0x140. Now, since this is a constant address, you cannot run a loop and in every iteration increment this address. It is not possible, right? If you are using the direct addressing mode in LDS instruction. However, this is possible when you are using, it is possible to use a loop and increment the address in every iteration of the loop when you are using the register indirect addressing mode in store or load instruction, strld instruction. Okay. Any questions? So this is like, just like for example, how you write arrays in C or Python or Java language. So what you do is that you need to know only the address of the first byte, and then in every iteration you just keep incrementing the address in the pointer register, which can be X, Y, or Z register. Okay, so there are some other variants of the same register indirect addressing mode, and that is basically using register indirect addressing mode with the displacement. Remember, in post increment and pre-decrement variant, we were changing the address only by 1 byte. Either we were incrementing by 1 byte, or we were decrementing by 1 byte. But what if we want to like not access the bytes in sequence? So let's say, for example, if I want to uh here, let me try to help you visualize this. So let's say you have these bytes in memory, right? And you have the starting address of this one. I'm just writing SA to indicate the starting address. So if we use the, let's say, post decrement variant, what will happen, that my first address will be SA, next one be SA, next one will be SA plus 1, next one will be SA plus 2, and so on, right? If I'm running a loop. But let's say I don't want to write on every byte. I want to write value in the first byte, and then I want to skip 2 bytes. Or let's say I want to, let's say I want to skip 2 bytes. and I want to then write the next byte after skipping 2, right? Which is basically plus 3, right? So for that kind of situation, you can use the register indirect with displacement. And here plus Q indicates the displacement. So here what is happening is, for example, in this case, store z plus 5 comma r20. So you are storing r20 in location which is indicated by z plus 5. What is z? Z is your pointer register. So whatever you have, again, let's say you have memory here, right? And there, this is some location in memory which is pointed by z, and this is your z register, right? And now when you will say, okay, store r20 in z plus 5, so it will be like, let's say I'm just saying it is address 10. Okay, so address will be changed by 5, so it will be now 0.2. So but the z will remain same, only the address will be first, 5 will be added to the current address, and then it will be used to access the memory, right? So here is how it is working. So first, definitely you load the address in the register, X, Y, or Z register, and then I'm not sure whether we can use X or not. Let me not state something I'm not sure about. I can check it later whether we can use X or not. But for now, let's stick to the statement that we can use only Y or Z register. Okay. So you put the address in Y or Z register, and then what you in the instruction itself, when, for example, store, you are specifying the displacement Q, and then this Q will be added to the current value of the pointer register, and then the resulting value will be used to access the memory location. And here Q can be a number between 0 and 63, so you cannot have a displacement of more than 63, because in the instruction format you have only 6 bits to specify Q. So if you have 6 bits to specify, the maximum value you can specify is 63. Similarly, you can also use load with this register in direct with displacement mode, also in the load instruction. And the D here in both store and load, it stands for store with displacement and load with displacement. So if you are using these modes, Z plus Q, then you must use uh, load with displacement and store with displacement. So for example, if you write only, if you don't put this D here, this D here in the load instruction, your assembler will complain. Any questions? Okay, so if no question, then let's go to the quiz. Week 10, day 2, quiz 7. Okay, go ahead. Okay, and let me end the poll and let me actually show you what is wrong with this code snippet. Okay, so where is OneNote? Yeah, I can simply write here. So first statement, first instruction is correct, R16. There is nothing wrong with it. Then the second one, what do you think about the second one? Anyone who want to respond? Is there anything wrong with the second instruction? Yes, you need to use load with displacement. Okay, because you cannot use +10 with only load. What is wrong with the third one? There are two issues. You need to use store with displacement and you cannot have displacement of greater than 80. So it should be a number less than or equal to 63, right? So that is also wrong. So let's say I'm putting some number which is less than 63 or 16. And what is wrong with the last one? Again, you need to do store with displacement x plus 10 or 17. Okay. Any questions? Okay. So this is just a screenshot from your textbook. So I just wanted to highlight some points here. So when you are saying, for example, when you are using post increment variant, so after loading location pointed to by after loading location pointed to by y, the y is incremented. So first you load the data from the location which is pointed by y and then increment the y. Okay. And similarly, in the pre-decrement variant, the y is decremented first, and then the location pointed to by y is loaded. But after decrement, so new location is like one less than y. So and from that resulting location, you read the data. Similarly, when you are saying load with load direct with load with displacement. So when you are saying y plus q, so what happened is that after loading location pointed to by y plus q, the y stays the same. So y is not changed. Remember, in y plus and minus y, the value of y is changed after the instruction, but in LDD, the value of y is not changed. You can also see it from this figure here. So the result of this addition is not fed back to y or z. But if you go back to those figures for increment and decrement, so here you can see that the result of addition or subtraction is fed back to register X, Y, or Z. So these are like important points which you need to keep in mind. Okay. Okay. So with that, we are done with our addressing modes. Any question you have before we move on to our next topic, which is about timers or and counters? No? Okay, so if no questions, then let's talk about timer and counters in AVR microcontroller, more specifically in the variant which we are using in lab at Mega 328P. Okay. So what is a counter register? So what you do in counter register, that it is simply a register which holds some value. You can initialize the register with a value. Let's say you can initialize it with 0 or 10 depending upon what is the size of the register. So if the size of the register is, let's say, 8-bit, you can initialize it with any value ranging from 0 to 255, right? So you can load the value into this register, right? So you can load the value, right? And then it has an input, clock input, so which can be a clock, or which can be an event, right? And whenever you have a positive whenever you have a clock, or let's say whenever you have a transition, right? on the event line, what happens that the current value of the register is incremented. So let's say if the current value we loaded, let's say 0 into this, right? So whenever there will be a transition on the input signal, so what will happen that the value will be incremented by 1, right? And that you can also read out that value. Okay. Oh, sorry, I'm circling the wrong line. So here you can read out the value. Okay. Other than that, whenever there is an overflow, whenever an overflow happens, there is an overflow flag which is set equal to 1. What does mean by overflow? So if we have an 8-bit counter, so the maximum value you can have in 8-bit counter is 255, right? So let's say the current value is 255 and another transition on this event line happens. So which means the value need to be incremented again. So when the value will be incremented again, what will happen? So it will change to 0. Why it will change it to 0? Because the binary of 255 is 8 ones, right? So when you add one more to 8 ones in binary, what you will get? You will get 8 zeros. Sorry. You will get 8 zeros and 1. But so in total 9, but we have an 8-bit register. So the value which is stored in the register is basically all zeros. So that's why we say an overflow happens from 255 to 0. So when an overflow will happen, this flag will be set equal to 1. Okay. So that is a counter. So what is the job of a counter? It accumulates the number of events happened. So like for example, if you started from 0 and every time there is an event happening, this 0 will be incremented. So at any given time, you can, by looking at the value of the counter register, you can tell how many time the event has happened, right? Unless that there is an overflow. Because if there is overflow, it is basically 256th event, right? But the register value will be set equal to 0, but you can detect it by looking at the overflow flag, right? So it overflows when some condition is met. So some condition is met basically mean like there is depending upon the size of the register, if there is an overflow. So it stores the number of events in a counter register. Any questions? Okay, let's say that we want to, for example, use the counter register to count people, right? So what we can do is like we can initially we can load some value, like for example 0 here. Then instead in on the event input we can connect a sensor which actually senses like which gives a positive signal or a high signal every time a person passes a particular location, right? Like for example, you have a door, entry door at a building, and then what happened that counter register will be incremented, right? So, and one other thing we are doing is that we are connecting the output of the counter register with the comparator, and the other input to the counter comparator is 4. So what is comparator will give us 1 when these two inputs of the comparator are same. So basically we are asking the comparator to tell us give us 1 when 4 we have counted the 4 people, right? So what we can do is that we can initialize the counter to 0 here, right? And then it is always counting. So when first person passes, sensor will give us a value of, let's say it will give us as a transition on the input signal. So 0 will be incremented to 1. When second person passes, another clock will arrive. So this will be then incremented to 2, but 2 and 4 are not equal. So on the output, we will still have 0. And then on third transition, this will be incremented to 3. And then on fourth transition, this will be incremented to 4. And at this point, the two inputs of the comparator will become equal to same, and they will be equal. And then the output of the comparator will be 1. So like we are saying, okay, we have detected 4 people, or let's say we just want to say, okay, what is the capacity of a room? So if there are 4 people, so we want to say, okay, the room is full. Okay, so any question here? Okay. So let's say that we want to have a second design about counting the people, doing the actually the same thing. We want to count 4 people. So what we can do is that we can initialize the counter uh, to 252. Why 252? Because the maximum value we can have is what? 255, right? And remember, an overflow happens when this value changes to 0, from 255 to 0, right? So if I initialize this counter with value of 252, and then every time a person passes, the value of the counter is incremented. So it will become from, if it is 252, then initially, then 1%. If first person passes, it will become 253. When second person will pass, it will become 254. And when